What's up?
The 3,000 is better until it goes after 10 years.
Until you get past 10 years, the $3,000 gives you pretty good money. Because by the time we get up to year 10, we should have, there it is. It was like if you kind of like this, where you started at year 0, that would be 80,000. And our percentile rate, once we make this jump here, that's not a 3, that's just a squiggle. We would be at 81,444 and change. I have about 73 cents, but it kind of depends on where you round. So if you started at year 0, year 10 should be about here. Because our $3,000 is just taking our $50,000 starting salary. And how are we getting this? What could we do for an equation? Yeah, we're adding $3,000 each year, whether it's X or Y or, so like X for X variable, Y for year, whatever. So we're adding $3,000 every year. So we took our $50,000, we added for 10 years, 3,000 times 10. What's happening with the percent? What's going on there? The percent keeps changing because we're needing to take 5% of all the things before it as well. So we still are starting with that $50,000, but every single time we did this, like I'm going to show a little bit over here. So we took our $50,000 times 5%, and then we added it to the $50,000, which then gave us our $52,000 times 5% that we added back to it. So every time we're taking the number we had before and the 5%, there we go. So that's the number we started with on this row. This is the number we started with on this row. We're taking that number times 1 plus that 5%, which typically we write it as a decimal, 0.05. What this is this getting us started towards exponential growth? Because we do this for every single row. And there is a way to do it without having to write every single row out so that we could calculate it for year 10, year 15, year 30. If I want to know what I'm going to get when I retire in 40 years, we could figure that out if we take what we started with, our very, very first year, our 1, because we're going to keep our salary and not lose it, plus our percent rate, 0.05, to the power of the year. So if we're using Y for year here, that's how we would set up this equation. We're going to talk in more detail about where all these pieces come from and what we use them for. You guys have done this in Algebra 2, but it's been a hot minute. So if we have this and we're planning to stay in this job forever, it is a forever job, dream job, we want to be here forever and ever, or it's with the dream company, we got a job at Google. Maybe, because they're supposed to have really nice work culture, really nice benefits. Living in California, we want to work at Google for the rest of our lives. Or we want to work at Disney for the rest of our lives. I would say take the percent raise. If we're at something that we're like, I don't know how long I'm going to be there. I'm happy here for a couple years, but I would really like to move to a different state. I would really rather not work at Tesla for the foreseeable future, Amazon for the foreseeable future. I would like to think that this is a limited term option. So we might take the flat rate because if you leave within 10 years, you're going to wind up making more money. 10 years is where it switched over here. So it really depends on what the rates are that they give you, but we can compare them. So what kinds of functions are these? What kinds of equations do we have here? This one here for our $3,000, what would this look like if we graphed it? 50,000 plus 3,000 y. Linear. This would be a line. So this is linear. What is it called when we have the variable in the exponent? Do you remember? It's in the exponent. It's called an exponential. And that's what this whole chapter is going to be about. We are going to be looking at exponential functions. Exponential functions are very, very, very much real life things. Not only are they how salaries and raises are calculated a lot of times, they're how bank accounts are set up, they're how credit cards are set up, they're how mortgages, student loans, all those things are set up. So we're going to look at a couple on the next page where we're going to practice this, and we're going to look at this kind of equation and all the pieces we need for it. So on the very next page, we're going to have this problem. So we've got that North Dakota has the fastest growing population out of all 50 states according to the data that they have here. So I don't know if 104 is in fact right page. Hang on a second. It is in fact the right page. Yay. So it's task number 1, growth and decay. And so on January of 2013, they said that they had 70,000 or 700,000 people in the state of North Dakota. They estimate that their population has been growing 5% a year. That's what they get from their data. So we want to see if we can estimate their population this year. This is the kind of formula that we're going to use. And these pieces up here are going to tell us a lot of information. So what A is standing for the amount, or the total amount. I'm just going to color code down here. This P here, what we use for that, the word for that is often principal. A-L, I think. And what that is it's the starting amount. It's the starting place. Or starting number of things, starting amount of money, the starting place. Our R is our rate. It's really, really important that we put it as a decimal. And then we have that our T is going to be time. This guy up here, our exponent. T is time. More often than not, it's going to be in years, but there are going to be times when we do smaller units of time. And it's just really going to be beneficial to think about it in terms of whatever story you have. So it's going to be some unit of time. We are also going to need to decide whether we use the plus or minus. We are not going to need to use both in problems. It's either going to get bigger and grow and we use the plus, or it's going to be smaller and it's going to do what we call decay. So growth or decay is when we get the plus or the minus. So looking at this story, we're going to see if we can find these pieces and figure out what all these pieces mean. So plus would be if we're growing or getting bigger. Minus is if it's decay or getting smaller. So let's look through this story again and see if we can figure out what pieces we have here. What do we know? Which one was it, the 700,000? The principal. It's our starting amount. We're starting with 700,000 people. That is where we start. So that is our principal. So wrong color. Blue. 700,000. There we go. I'm just going to give us pieces. The one's going to be there. Are we growing or decaying? Growing. And we can tell that because it used the word growing. Right up there at the top, it says growing up here. So we know it's getting bigger, so we're going to use the plus. What is our rate? 5%. How do I write 5% as a decimal? 0.05 or 0.05. Per cent, there's 100 cents in a dollar, so per 100 is how we do that. So if you don't remember that, take 5 and divide it by 100. 5 per cents in a dollar. 5 per 100. So it's our 0.05. The total amount is what we're being asked to find. So our last piece to figure out before we can start, like, mathing, is we need to figure out the time. What is t going to be?
12.
What makes you say 12?
It says this year,
So this year,
2025, so there's 12 years between 2013 and 2020.
yeah, they started in 2013. So we need to know how much time has passed since they collected this data, since they figured out how many people they have. So this 2013 takes 12 years for it to get to this year, 2025. So it's all about how much time has passed. Don't put the year in there. It's how much time has changed. So when we're doing this, a lot of times we're going to type these things in the calculator, but I do want us to simplify this bit for a particular reason that we're going to go through later this week. So I want to simplify this guy, and we're going to add together our 1 plus 0.05. So we're going to have our 700,000. 1 plus 0.05 is 1.05 to the power of 12. And so to get this value, we're going to type this sucker in the calculator. So I'm going to grab my calculator. We're going to take our 700,000. 1, 2, 3, 4, 5. There we go. And we can just straight up type it in like this. 1.05. Boop. Close my parentheses. Our button that gets us up to the exponent where we can type any number is that little arrow right there. Lit up red right here. It's called a caret. That puts us up into our any exponents, and I can put in my 12. So we can see that they would have, theoretically, if their population stayed growing at this consistent rate, 1,257,099.428. Yes, dear.
Do we still do the thing where we don't round up?
I was going to say, that was going to be my question. What are we talking about here as far as the story goes? People. So how many people do we have here? Can we have 0.428 of a human? No, you're tossing random body parts into town square. I do think it would affect our population. Do not toss a random leg into town. If I toss 0.4 of a person, that means I probably tossed a leg and an arm into this group of people. I do think they might start to run. It's probably going to change the number of people in the room or state if people start tossing random limbs in. And don't tell me a child counts as a half person. So when we have living creatures, we are going to always round to a whole unit. It's okay to round, but don't give me a part of a person, a part of an elephant, a part of a rhinoceros. I don't even care if it's a mosquito. Don't give me a part of a mosquito. Okay, so on this one we had our 1 million. Oh, and now I have no clue what that number was. I have said too many things since then. 257,099. 27099 people. Okay, so a lot of this is going to be finding the pieces in the story. So we're going to look at number 2 as well. Questions on this one? This is the first time we've done an exponential in probably a year. Whoop, that's not what I wanted. So let's look at number 2. Let me show up on here. I didn't give myself a page to do it. Love it. So we've got on this air freshener, number 2 on here, that has 30 grams of fluid when it starts. And the fluid amount in the bottle decreases by 12% per day. And we're going to try and write a generic equation, and then let's see how many ounces of fluid are left in maybe 15 days. So we have 30 grams of fluid to begin. Decreases by 12% per day. This is just exactly what you guys have in there. I'm just cutting out a few words. Find equation for T days. And then this is not in there. We're going to estimate for 15 days. So see if we can come up with an equation here. What do we think? I'm going to put that formula up here again. See what we think. What's our principal going to be? The 30. So we're going to start with the 30. Is this going to grow or decay? Decay, because it's decreasing. We know that, so we use our minus. What's our rate? 12%. So as a decimal, we put it as that 0.12%. Per 100, so when in doubt, divide it by 100. That puts you down as a decimal. And then for our kind of generic equation, if we want to know what's happening in T days, we just leave the T up there. Yeah, I gotta hook the T, otherwise it looks like a plus. There we go. Yeah. So if we want to estimate how much fluid is left after 15 days, all we got to do is simplify this a little bit. So we're going to have our 30. We can do our 1 minus 0.12. What is 1 minus 0.12? Yep, 0.88. And we're going to estimate this for 15 days. So how much fluid is left in our air freshener after 15 days? Yeah, 4.41, 4.4, depends on where we round, honestly. I'm going to go with 4.41 grams. When we have a unit of weight or volume or something like that, we can absolutely have decimals. Totally fine. More often than not, it's going to be money, which we will round to 2 decimal places, or it's going to be living creatures, where we round to the nearest whole unit. If it's in between things, I will try my best to get it to make sure we tell you where to round. But for money, we always round to 2 decimal places because that's where cents go. And for living creatures, any living creature, no matter your opinion on the living creature, they get whole units because we are going to be ethical and not throw random limbs into collections of things. Okay, so we're going to be starting to look at all these exponential functions. There's not that many pages left in your workbook. Like, this is all we got left, y'all. That's all we got. You have 31 days. So don't check out yet. Please. We still got stuff to do. So the first homework of this chapter is very much based on what we just did. It is, let me see. It's very, very much based on what we just did. Okay? Oh. Ew, they want us to sketch a graph. Oh my god. Is that on mine? Why is it listed as page 108? That is not the right page number.